Hey, Suparna.
Hi.
Hello, hello.
Can you hear me?
Oh, yes, I can hear you now. Yes, can you hear me?
Yes.
That's good, that's good. Um, so I made like a little outline on like what we could go over for midterm one material for 118C, like the 118A-B review, and then we could go into the carboxylic acid derivatives, and then these reactions here. And then after that we could summarize and do practice. And I'm like skipping over the nomenclature stuff and acid-based stuff right now. But then if you have any questions on that when you like review them, you could come by and ask questions about that, and or we could do practice on those after we finish the reactions and mechanisms and synthesis here. Right.
Okay,
Okay.
sounds good.
Yeah. Is there anything you wanted to get started with, or like any questions that you have?
No, not at the moment.
Uh-huh. Okay, okay, that's good. So, let's do the 118A and B review. We did the organometallic and hydride reagents already. Now let's move on to the 118B review, which is going to be like addition, elimination, substitution mechanism. So that's going to be in acidic and basic conditions. So let's talk about that. Addition, elimination, aka substitution mechanism. And this is the general mechanism for most of these reactions in the midterm one. All right. So there. And there's two conditions. There's basic conditions and acidic conditions. Let's look at the example in basic conditions. So generally, you're going to have a carbonyl that is attached to some sort of leaving group. And this leaving group here could be halogen X. It could be carboxylate. It could be OR group, like an ester. Or it could be a amine group making the amide. Right? So these are just different leaving groups that this carbonyl can have. Right? And depending on what leaving group it is, that's going to give you a type of derivative. Right? Like if it's a halogen, that's an acyl halide. If it's a carboxylate, that's anhydride. If it's an OR group, that's an ester. If it's an amine group, that's amide. Right? So in basic conditions, everything is going to be negatively charged. Right? So you're going to have your nucleophile that's negatively charged right there, which is going to attack this carbonyl, push the one into the oxygen, and we're gonna get this intermediate right here. We're gonna have an O minus and a nucleophile right there, giving us this tetrahedral intermediate. Right now, once we have this tetrahedral intermediate, usually like if this was an aldehyde or ketone, we do acid workup, right? Like this O minus becomes an OH by grabbing a hydrogen from acid source like H3O plus. But in this case right here, we're not going to do that yet, right? We have a leaving group present, so we're going to reform the carbonyl, right? By using one of the three pairs of electrons on oxygen here to go down to create a double bond between this carbon and oxygen and kick out that leaving group right there. We have to kick that out because we want to conserve the octet row of that carbon right there. Right, so when we kick that out, we're going to get this right here, the carbonyl back and the nucleophile right there. Right, and then the leaving group that left is going to leave with a negative charge if it was neutral. Right, that's because this bond right here has two electrons. Those two electrons are breaking off onto the leaving group, giving that leaving group a pair of electrons, and if it was neutral, it's going to be negatively charged. So this is an addition elimination mechanism or a substitution mechanism because we see that the leaving group here was substituted with the nucleophile. Right, it's also called addition elimination because the first step here is addition. Right, we added the nucleophile onto the carbonyl, creating us this tetrahedral intermediate. And then the second step here was elimination, when we eliminated the leaving group, when we reformed the carbonyl. Okay, so that's the addition elimination or substitution mechanism in basic conditions. That's the short mechanism. The longer mechanism would be in acidic conditions, and let me show you that right now. So let's look at acidic conditions. Okay. Now in acidic conditions, usually the leaving group will have a proton attached to it, a hydrogen right there. That's for most derivatives. I'm gonna show you when, like, you won't see that proton, but just to keep it general and apply to most examples, you're gonna see this leaving group here is gonna have a proton, right? And our nucleophile here is also gonna have a proton. And we're in acidic conditions, so most likely for Helix class, he likes using H2SO4 as the acid. Now, before, in the basic conditions, this nucleophile here was a strong nucleophile because it had a full negative charge, which makes it a strong nucleophile and able to attack this electrophile right away by itself, right? But now, if you look at this nucleophile right here in acidic conditions, there's no full negative charge anywhere. That nucleophile molecule is neutral, so it's a weak nucleophile. This weak nucleophile here cannot attack the carbonyl directly like that. That would not happen, right? Because this is a weak nucleophile. This is a weak electrophile. Weak molecules cannot react with other weak molecules. So what's going to happen first in acidic conditions is that we're going to protonate the carbonyl oxygen with the strong acid we have. So I'm going to draw out my H2SO4 out like this. This carbonyl oxygen here is going to grab a hydrogen from the acid, kick out the conjugate base, and give me this protonated carbonyl here. Where this oxygen, because it gained a bond to hydrogen, is now positively charged, right? Oxygen with 3 bonds and 1 pair of electrons is going to have a formal charge of +1. Now, this formal charge of +1 right here activated the carbonyl, right? Before, this carbonyl right here was partial positive charge, right? Because of the electronegativity of this oxygen. But because this oxygen is very angry now, like it doesn't like having that positive charge, it's going to want to withdraw, pull on the electrons of that carbon even more, making this carbon activated, right? Making it more electrophilic, a stronger electrophile, more positively charged, right? Now, because this is a strong electrophile, the weak nucleophile is now able to attack this strong and activated electrophile and push the double bond onto the oxygen to give us this tetrahedral intermediate here. Okay. Now, once we have this tetrahedral intermediate, we see that we want to eventually kick off this leaving group and keep this new group that we just added in right there, right? But right now, this is a good leaving group. This is a bad leaving group. And we want to make this into a bad leaving group, and we want to make this into a good leaving group. So there's 2 ways that you can do this here. There's a short way, which Helix allows, and there's a long way, which like he will also accept that. But let's do the short way, which is quicker. We can protonate this leaving group and deprotonate that group at the same time, giving us this tetrahedral intermediate here. Wait. Yeah. This leaving group here, yeah, it doesn't have to have a hydrogen. So let me just erase this proton for the leaving group. I just realized it did not need to have that hydrogen. The thing that needed the hydrogen here was this nucleophile. Okay. And then this leaving group here gains the hydrogen from the nucleophile. Right? If I highlight this hydrogen here of the nucleophile in yellow, that's that yellow highlighted hydrogen right there. Now, we made this into a good leaving group. We made this into a bad leaving group. That's good. That's what we want. Right? We did that by having this leaving group grab the hydrogen from this nucleophile. The bond between that hydrogen and nucleophile, there's 2 electrons there. Those 2 electrons pop onto the nucleophile, making it neutral, right? It was positive charge before, but it became neutral when it gained that pair of electrons from that bond right there. Once we have this desired tetrahedral intermediate, we could drive off the good leaving group by reforming the carbonyl and kicking off the leaving group like that, giving us this final intermediate here. Right, and the leaving group would be now neutral with its hydrogen like that. Okay. Now, the final step here is to bring in the conjugate base HSO4 minus that we formed in the very first step here to come and deprotonate and neutralize the positive charged oxygen, giving us our final answer. And our acid catalyst, H2SO4, gets reformed here, but you don't have to include this in the predicted product. Okay, so yeah, the acidic conditions mechanism for this is gonna be longer than basic conditions, right? Basic conditions is a simple 1-2 step addition elimination, but acidic conditions it's like longer because we have to activate this weak electrophile in order to start the reaction, right? And Murray Jones, she made a really good acronym for this acidic conditions, peptide, right? Where the first step is protonate, second step is addition. Next two letters are proton transfer, and then elimination, and then deprotonation. But that is more for like Nisiri and the professor or Wei who don't allow you to use note cards for the test, right? That this is like good for that. But Helix allows you to use a note card, so you could just put the mechanisms on your note card and refer to that, right? And oh yeah, I just remind me after this session, like office hours, I'm gonna send you a note card for the midterm one reactions and mechanisms for Helix.
God, really?
Yeah.
Thank you.
Of course. It has like the reactions and mechanisms you need to know, but it doesn't have the nomenclature or like acid-based stuff. Just the reactions and mechanisms.
That's good enough. That's what I need anyway.
Okay. Any questions on the mechanism here in either acidic or basic conditions?
Yeah, can you just explain one more time how it became a strong electrophile?
Yeah. So let me add a new page here and show you a concrete example where the leaving group is now going to be this OR group. And I'm going to give you a concrete nucleophile, which is going to be this OR minus group and the solvent right there. Now, this electrophile here is a electrophile, but it's weak, right? Like it's not as positive charged as it can be. The reason why it's an electrophile is because this electronegative oxygen here is pulling on its electrons, making it positively charged. This molecule here with the negative charge is strong nucleophile because it has that full negative charge right there. That full negative charge is going to attack that carbon, push the double bond onto the oxygen, and give us this tetrahedral intermediate. This is able to happen because this is a strong nucleophile directly attacking this weak electrophile. Now, the next step here is elimination because we're in basic conditions here. So we're going to reform the carbonyl and we're going to kick out the old OR group to give us this new group here. Right? And basically what we did here was we substituted that old leaving group with this nucleophile right there. This is a name of reaction called transesterification, which you will learn eventually. Esterification. Right? That's because this ester here, this ester became a new ester or a different ester. Trans meaning different, so we created a different ester from an ester. So transesterification. Okay, so let's talk about the weak electrophile one in acidic conditions. If we have that ester with this ester in acidic conditions, H2SO4. Well, actually, let's not add the H2SO4 just yet. This alone would give no reaction, right? That's because this electrophile here is weak. This nucleophile here is weak. There's no full negative charge on that nucleophile. So this oxygen here, even though it has 2 pairs of electrons, it cannot directly attack the electrophile because it's weak, right? But once we add acid in it and we protonate the carbonyl oxygen like this to make this into a stronger electrophile. This is now a stronger electrophile because I'm going to draw you out the resonance structure here, down here. right? We could push this double bond onto the oxygen to give us this resonance structure right here. Right? Where we see that this carbon here has a full positive charge, making it more electrophilic, more positively charged, right? Now you could say that it's the same for like this structure as well, right? But if you were to just draw out the resonance structure of this like that by pushing the double bond onto the oxygen, you will get a positive charge on the carbon as well, right? But this positive charge right here on the carbon is stabilized by the negative charge on this oxygen here, right? This is the molecule where we did not protonate the carbon to oxygen. This is in basic conditions, right? We still can do resonance here, giving that carbon a full positive charge, but it's a weak positive charge because it's stabilized by that negative charge on oxygen right there. If we look back at the acidic conditions right here, and we see the resonance structure of this, when we push the double bond onto the oxygen here, this positive charge is not stabilized by any negative charge anymore. So that's why it's less stable. It's more reactive, more electrophilic.
Got it.
Right. Any questions on that?
No.
So that's why another way that you can think about it is that this positive charge oxygen here is very angry, right? It's very unstable right now because it does not want that positive charge. So it's gonna want to pull on the electrons way more on the carbon. And if it pulls on the carbon electrons way more, this carbon becomes more positively charged. And when it becomes more positively charged, it becomes a stronger electrophile, right? Okay. Now, to finish this mechanism, I'm gonna bring in the weak nucleophile, which is now able to attack that strong electrophile to create this tetrahedral intermediate here. Any questions on how I got to this tetrahedral intermediate right there?
No.
Now, this is the new bond right here. This is the nucleophile that attacked. This is the old group. We want to make this into a good leaving group because we want to eventually kick that off, that old group off. We want to make this into a bad leaving group because we want to keep that. So we could kill two birds with one stone here. We could protonate the old group and deprotonate the new group, right? And that's gonna reverse our leaving group ability here. We converted the good leaving group into a bad leaving group, and then we converted the bad leaving group into a good leaving group. Now, once everything is in place, we can reform the carbonyl from the alcohol, kick out the good leaving group that we want to kick out, get this tetrahedral intermediate. Leaving group is right there. Last step is to deprotonate the positive charge oxygen to make it neutral. Like that. Now, the proton transfer steps, right? There's 2 points that you should keep in mind when you do this mechanism. You're always gonna deprotonate the group you want to keep, and you want to protonate the group you want to kick out. Kick out, right? Now this is like the end of 1 B when we talked about imines, enamines, hemiacetals, acetals. That comes back here in this unit, carboxylic acids, right? That's when we get the tetrahedral intermediate, which is this right here. We see that we deprotonated this group right here to convert that into a bad leaving group because we want to keep that group. We protonated this group right here, right? Because we want to convert that into a good leaving group, positive charge. Like a proton is a hydrogen, right? Protonate, give a hydrogen. Deprotonate, take away a hydrogen. So those 2 points right there will come again for acidic conditions mechanisms for this unit. Okay. Any questions on that one?
No.
Okay. Now I'm gonna give you a practice problem on what we just did right here, and then I'm gonna go to 118B for Kelly. Okay. Let's see. This one here is gonna be a little bit trickier one, Suprana, because I did not show you this one yet, like this specific reaction, but it follows the same mechanism as the acidic conditions addition and elimination. Right. So it's gonna be something like this. And if you get stuck, just let me know. When I come back to this problem, and I could walk you through it. Ooh, actually, no, that's gonna be problematic. I just realized for this in acidic conditions. So instead of that, let's make this into carboxylic acid. Now this is gonna be more doable. Okay. Try this reaction, predict the product, and draw the mechanism. The step-by-step arrow by arrow mechanism. Arrow pushing mechanism.
Got it. Thank you.
Yep. And I will also show you a shortcut on how to predict these products too after this. Right. Okay. Hey Kelly, did you have lecture yet for 118B Cagley?
Yep.
When do you have the lectures this quarter for Cagley 118B?
Monday, Wednesday, Friday.
Monday, Wednesday, Friday, 15 minutes. I see. Was it just syllabus day? Did she go over anything new, or did she do 118A review?
She did alkene naming.
Oh, alkene namings. Yeah, that's the very first part of 118B alkenes. Did she go over any properties or reactions?
No. She went
No.
over the syllabus and then the alkenes.
Naming. I see. Okay. Let me create a Google Drive folder and send it to you so that you could post the lecture notes there, and then I could access it when I teach you, I could access those notes. Let's see. Because I think you're the only like 118B student that I know.
Wow.
I know like everyone else is 118C.
I'm the loner.
No.
I think maybe because
I think because like the newer OChem students, they don't know who I am.
that
Because I wasn't in Davis. I'm not in Davis, and then like because I graduated from Davis like a year ago, like 2024. And I
yeah,
think it's like I'm slowly like going off grid out from the campus. People not trusting me anymore.
you're being forgotten.
Yeah, it's okay. Let's see. Kelly.
A lot of people didn't get into 118B either
Oh, for Cagley?
because it's only one section.
Oh yeah, like my sister is taking 118B right now with Cagley, and she was not supposed to get in. Like she was in the wait list, right?
Oh.
And then a student coordinator like emailed her about a PTA number, right? And then like she dropped the class because she was the waitlist, and because they told her to drop the class and register for a different section. And then she tried putting that PTA number in, but then it did not work. It said somebody used it already, so she thought she got like tricked by someone. So then she asked me what to do, and I told her to email the guy, and then if he doesn't respond, like call him like a day or 2 days after. But then luckily he responded the morning after, and I gave her a new PTA number that worked. So that's good. I thought someone tricked her. I thought someone pretended to be like the student coordinator and tricked her.
The head TA?
Not head TA. It's like a student coordinator. I don't know.
Oh.
It's like not in the chemistry department. It's like something else.
Interesting.
Yeah. It looked pretty sketchy too. But then like I told her to search up the guy's name on UC Davis, and then like it looked official. So I was like, I don't know. Let's see. Okay, let me do notes. And then practice exams as a subfolder, so then I can look at that too. Okay. Can you send me a message on what email you want me to send this folder to on Zoom or text? And then I'll go over alkene reactions with you, because I don't really focus on nomenclature or naming that much, but we can go over that if you have questions on that.
I texted it to you.
Okay. Let me get my phone. Be right back. I am back.
You never have your phones.
I know, and it's always away from me, so I don't get distracted when I'm like tutoring or studying or something.
There's something called silencing.
Silencing, but then the notifications, like when it pops up, and then like when it's phone is like nearby, like I have the urge to pick it up,
You should flip it over.
Oh my gosh! Oh yeah, you're right. Let's see. Okay. This one editor notify. Oh yes, and let me also send you my pre and post slots for 118B, so you don't have to focus on that.
Your what?
The pre and post labs, like lab flow. So then you could just look at that and just save time, save a lot of time. Okay. Yeah. But when I took the labs, it was PDF. We didn't have that lab flow website, but it should be the same lab with the same questions. So Parna, did I send you the 118C labs?
No, but you totally should, because that sounds really good.
Okay, yes. I'll send it to you. What email do you want me to send it to?
Hold on, I'll send you one.
Okay. Let's see. Let's see. Actually, let me just send you the midterm 1 stuff right now. My note card and the previous Helix exams.
Okay, I just sent you my email on Discord.
Okay.
It uploaded.
Yes, thank you. Playlists and the practice exams I have for it from spring 2023. The 2024 ones I don't have. But he'll probably post the 2024 practice on your guys' canvas. And when he does, can you guys send it to me so I can build up my pile of official resources?
For Helix or for
both?
But yeah.
Yeah, Cagley is a new professor here, so she probably uses Leaven stuff right now.
Unfortunately.
Oh my god.
Like all the vocab stuff, right? Like Kelly, like from Leaven's, that's a nightmare.
She just used Waze canvas.
Oh, now she's using Waze this quarter?
No, last quarter she just copy and pasted Waze canvas.
Oh, she copied and pasted the Waze canvas and she used Leaven's practice resources.
I think it was already on there.
Oh my gosh. Oh, I think Wei used Leaven's resources too. That's why. Yeah, I just sent you the note card, study list, and practice exams I have for midterm 1, Sufarna.
Oh my god.
And let me see. Listen, this one, send. Okay. It should email you soon. Let me see here. Kelly. Lecture notes, lecture 1 annotated. Ooh. Oh my god. The cheating plagiarism lecture slide, that one bullet point, don't do it, it's not worth it. Helix has the exact same phrase. Don't do it, it's not worth it.
Yeah, he says that. Yeah.
And then that's the paragraph underneath, cheating or plagiarism will result in referral to SJA. Yeah. Yeah. Review 118A.
Oh my god, I literally love you.
Yeah. I'm glad. It's gonna save a lot of time for sure, so you don't have to like worry about stuff that's not tested on the exam and then focus more.
Actually so useless.
I know it is.
I think did we tell you that in summer session our lab average was like a 55 to 60 and the TAs never graded until the second to last week of summer session, and I got so upset because they would tell me like, Saprina, don't do this next time, don't do that. I'm like, what do you mean next time? There's no next time. Like, I finished.
Yeah, I know. Oh my god. Uh, it was a struggle for sure. Let's see. Oh my gosh, so much nomenclature. And nomenclature is important. Oh dang, lecture 1 is all about naming.
Yeah.
No reactions. Okay. Let's see here. Let me go to my 118B folder. Go over some review with you for 118A. Okay. So there's gonna be 2 big ways to form alkenes, right? So let me categorize that right now. Alkene synthesis. And you learned about these 2 in 118A. The first way is going to be E2 or E1, elimination reaction.
You spelled synthesis wrong.
Oh my gosh, synthesis. Oh my gosh, the next way is gonna be alcohol dehydration. Okay. Now, did she go over anti-periplanar transition state in 118A?
Briefly, very, very briefly.
Very, very briefly.
Just like what it is, and that was it.
Okay. So let's look deeper into the E2 reaction. E1 is gonna be something else, but mainly we're gonna focus on E2. If we have this halo alkane right here, and we reacted with 2 different types of bases. The first type of base is going to be NaOH, or actually, let me just use NaOCH3, CH3OH, and the other one is going to be, let's say, NaOCCH3, and then it's solvent CH3,3COH. Right. Do you know what's gonna happen between the first reagent and this halo alkane right here?
It replaces the bromine?
That's SN2, right? Like,
Oh.
if you think of OCH3 minus right here, this is a strong base, strong nucleophile. If it's a strong base, strong nucleophile on a secondary halo alkane, we're gonna focus on E2, elimination, right? And this right here specifically is a small base, unhindered base. So we're gonna look to make the more stable alkene, the Zaitsev E2 reaction. So I'm gonna draw out 2 different possible hydrogens for you. Let's say this is hydrogen A, and this is hydrogen B. Which hydrogen do you think this OCH3 minus wants to grab to make the more stable alkene?
B.
Yes, the more substituted hydrogen will make the more substituted alkene. So that's the Zaitsev E2 reaction. Grab that hydrogen. The bond between hydrogen being grabbed and that carbon right there is going to make a double bond right here. Kick out that leaving group bromine to give us this alkene here. The methyl is still there, but it became a flat bond, right? It was wedged before, but it became a flat bond because we converted an sp3 carbon into an sp2 carbon right there, which makes everything flat and planar there. Now, I'm gonna draw out the second reagent out like this, and the name of this reagent is tert-butoxide, right? This tert-butoxide is also a strong base, strong nucleophile, so it's gonna also want to do E2 with a secondary halo alkane, right? But it's not small enough to grab this desired substituted hydrogen because this is too bulky. It's hindered. It's too big to fit in there, right? So what it's gonna do, it's gonna grab the most available hydrogen, which is the less sterically hindered side, hydrogen A, create a double bond there, kick out the leaving group, and let me do it in different colors to make it more clear. Let's do this. Grab that less substituted hydrogen, create a double bond there, kick that out, and give us our less substituted alkene. The methyl group here stays as a wedge because nothing touched that carbon. This carbon stays sp3 hybridized. So that wedge carbon stays as a wedge right there. Right. So that is one big way to form an alkene reaction. And there are some examples where it gets more tricky, right? Because the hydrogen and the leaving group has to be anti to each other, right? They have to be opposite from each other. Like if the bromine is a wedge, the hydrogen has to be a dash for the elimination reaction to work. If this methyl was a dash and this hydrogen was a wedge, you would have to do some rotation in the molecule to make it work. But before I teach you that, I don't want to overwhelm you with the stuff that you don't need to know. So I'm gonna wait until Cagley goes over this, and then I'm gonna see her lecture notes and see if she teaches this. Eliminate
Good.
anti yeah, because like if I teach you it and then you don't need to know it, then you learn it for nothing for Cagley's class. Right. Now, alcohol dehydration, I'm just gonna give you the simple one as well, and look at the other ones after, right? So for alcohol dehydration, let's say we have this alcohol right here, and I give you acid and heat. What do you think is going to happen in the very first step? What is the strong acid going to do in this molecule?
How am I supposed to know after spring break?
Okay, it's okay. When you see a strong acid, think of an acid-base reaction.
Isn't that a weak acid?
This is a strong acid. Sulfuric acid. H2SO4 is a strong acid. Weak acid would be like HF. Strong acids would be H2SO4, HCl, HBr, HI, H3PO4. H2SO4 is a common strong acid. Right. This strong acid here, or an H2O plus is also like another common acid. is going to look for the most basic atom. The most basic atom here is the oxygen of the alcohol. So the very first step of the mechanism is to protonate the alcohol by having this oxygen here grab a hydrogen from the strong acid and kick out a conjugate base. So like the term is protonate and deprotonate. Think of it like an action word, right? Protonate meaning giving a hydrogen, deprotonate meaning take away a hydrogen. If something gets protonated, something else has to get deprotonated. This OH is getting protonated, this acid is getting deprotonated, which is going to give us this this intermediate, not tetrahedral intermediate. Tetrahedral intermediate is something else. Right? Now, this OH here was a bad leaving group. We converted it into a good leaving group. That water molecule right there. This water molecule right here is just going to leave by itself to form. Do you remember the name of the intermediate? Like what charge would this carbon have as a result of this whole group leaving right here? What would have a positive or negative charge?
Carbocation?
Yes, carbocation intermediate, positive charge, right. Now, when we have this carbocation intermediate, do you remember that sneaky step that a lot of students forget about before we move on to the next step? Like once we have this carbocation intermediate, what's that one step we always have to look out for?
Hydride shift?
Yeah, hydride shift. And we could do that on the left side, right? Because right now, this is a secondary carbocation. To the right is a primary position. To the left is a tertiary position. So we could do a hydride shift on the left side by drawing out that invisible hydrogen, moving that invisible bond with the invisible hydrogen over there, which shifts the carbocation at the more stable tertiary position right there. That's good. Now, once we have this, we're going to do an E1 reaction, right? And the base that's going to do that is the HSO4 minus that we formed in the very first step right here. Now, there's 3 hydrogens that you could grab. You could grab hydrogen A, hydrogen B, or hydrogen C. Which one would lead you to the more stable alkene, more substituted alkene?
A?
Yes. So this conjugate base is going to grab A. The bond between A and that carbon is going to make a double bond right there. And that's it. There's no leaving group to kick out. It's not E2. Right. And that's going to give us this alkene. The tetra substituted alkene, because there's 4 groups around the alkene. 1, 2, 3, 4. Yeah, so that's another big way to form alkene. And the heat here is very important, right? Because if you had like low heat or no heat, you're gonna do something else. You're gonna do SN1. But let's just say there's heat here, and some professors give you like a certain temperature, like 180 degrees Celsius or something like that. Some professors just give you the triangle, the delta symbol, the heat symbol. We'll see what Kaggle uses when she goes over this. Okay, ready for practice problems, Kelly?
No.
No. It's okay. It's okay. You're gonna hop into them, and then I'm gonna check it at the end. Let's see.
Does it have to be all drawings?
All drawings? Like, what do you mean all drawings?
Like the what's it called? Reagents.
Reagents? Oh, usually they give it, well, Levens. Levens gives it to you in the condensed formula, like the writing form, right? Helix gives it in the drawing form, like the bond line form. Cagley, since she follows Way, in the way in this series are the same, and like she uses Levin stuff, she probably uses the condensed formula, right? You're used to seeing the condensed formula, the writing form, right? On the arrow.
Know. I don't remember.
Oh my gosh, yeah. So, you're probably not gonna see something like this on the exam, like the drawing form, the bond line form. You're probably gonna see it in like the condensed formula, the letters, the numbers.
Yay.
But I like saying it in drawing form because it's much easier to read.
That's great.
Yeah, that's that nomenclature, like condensed formula, bond line formula, QQE. Okay, that's one. And I want you to also try.
More?
Mm-hmm.
Trying to torture me?
That's what I gotta do to make sure you get that A this quarter. Oh shit.
Oh my god, flashback.
Uh-huh.
This is giving me
Flashback
PTSD.
PTSD from this one. This is all 118V stuff. Like, oh my gosh.
Is that a hexagon?
Huh?
Is that a hexagon? 1, 2.
This
3,
one?
4, 5. Yeah.
Yeah, it's a hexagon with alternating double bonds. The name of this structure is a benzene. Benzene. Wait, hexagon with like alternating double bonds is benzene.
It did not look like a hexagon.
Oh, oh my gosh.
Oh my god, you're roasting him out here.
You can't tell me when you're tired.
Poor Brian.
That's my job.
Oh my gosh. I'm being roasted out here.
Kelly, don't worry, 118's not that bad.
I think that's
I'm
because
telling
you're
you, if I
finished.
can do it, you can do it. I promise you.
Why does everyone say that?
Yes, Kelly.
No.
You can do it.
That's too sad.
Just wait till you get to like Deal's Alder.
Yeah,
Those are
Deal's
actually not
Order.
that bad.
Deal's
To what?
Order?
What's that?
That's later. That's the middle of the quarter.
Oh.
You're not gonna like the end.
It's actually kind of fun. Like the way Bryant explains it, it's actually kind of fun.
That means it's not fun.
What? Oh my god, I'm being roasted. When you get into
oh my god, no, I'm not even being sarcastic. I'm not even being sarcastic. Like
yes. Benzene, did you have fun with benzene so far now with like the ortho meta para directing groups?
that actually wasn't so bad. Like I actually like spectrometry.
Spectrometry, yes. Wait.
I like IR. I like those things. What I don't like is synthesis.
Oh my god, that's my favorite part, synthesis.
Oh my god.
I love synthesis.
Especially leave-in synthesis. She gives you like, she doesn't let you do your own thing. Like if I could just do my own thing, I could get the product. But she's like, you have 3 steps, and I'm like, no.
Yeah, I know. Like Helix will let you do your own thing as long as it works, and then you can get free credit. Yeah, he does. This not restricted.
Oh my god.
Yes.
Helix is sounding like a godsend compared to leave-ins.
He is. He's more laid back and chill. Like I don't know if you went to his lecture, right? Like he's more like slow. He takes his time with it. He allows a lot of time for students to ask questions, practice. But Levin, she's like on the go, like explaining like in detail, like super fast.
I know. I never attended a single lecture in summer session. I just went to your stuff, and then I did a lot of Maria Jones.
Oh my gosh, that's good.
Can you scroll up?
Yeah.
Is this part here? Or okay, yeah. This is the
other part too.
Yeah.
Okay.
Oh my gosh! I just get ready for the end of 118V.
Don't say that.
Don't scare her now.
I think Brian's meaner.
Oh my gosh! I have to.
Yeah, the end is rough. I won't lie. The end is very rough.
Yeah.
He thought I was in 118C.
No, that's because most of the people I teach are 118C. Like I forgot. But now I know, Kelly. That was last quarter. Now
Sure.
I remember.
That was like last week.
Yeah.
Shame.
No. Okay. Supana, oh yeah, let me see your work here.
Yeah, I'm done.
Okay, okay.
I won't lie, I did get confused during the protonating and deprotonating because that
Mhm.
abomination of a nucleophile you gave me
This one, yes, yes.
was not easy to work with. I feel like I created a new carbon bond, but I can't tell.
Uh-huh. Can you send me your work on Discord or yeah,
Yeah,
Discord?
it's ugly, but yeah.
Let's see. Let's see. Okay. Okay, so I see. First step is correct. Protonate the carbonyl oxygen to make that into a stronger electrophile, activated electrophile. What's your nucleophile here? What are you using as the nucleophile? Like what is attacking that carbonyl?
The carbon.
Not the carbon because there's no pairs of electrons
Oh,
there. It's a different atom.
it's
But
oxygen.
yes, it's gonna be that oxygen. So
Oops.
let's try that. Right, because a nucleophile is gonna have like a pair of electrons to attack an electrophile. That carbon has zero pairs of electrons, for it to attack. And what is the partial charge of that carbon? Like, is it partial positive or partial negative?
Yeah, it's partial positive, so
Yep,
it
yeah.
can't even be a nucleophile.
Right,
Oops.
right.
Okay.
Yeah, yeah. That's good. Like, it's want to see A stuff coming back.
Yeah, it's been forever.
It's okay. Like
They should just
someone,
let people.
yeah.
They should just let people like take classes when they need to.
When I need to, I know. Like you wanted to take it like fall quarter, right? Right after you took 118B.
I wanted to take it fall, and then they didn't offer it in winter, and I had no choice but to take it in spring.
Spring, yeah. Oh my god.
I was so ready for fall too. I was practicing, and I was like, I got this.
Big gap. Yeah, there's just one person I'm teaching right now. She's taking 118C this quarter, and the last time she took 118B was last spring 2024 with Mascal.
Holy
So it's
shit.
been a whole year. It's been a whole year. And someone else, like, is like was like in your situation. She took 118B with Levens over the summer session too, and then she's taking 118C with Helix this quarter.
I have like 3 other people that I know are doing it too, like with me.
Oh, right. Like the same thing as you. Oh my gosh.
Yeah,
Dang, what the heck?
because we all didn't get it fall quarter.
Because of the waitlist, right?
Yeah.
Oh my god. Okay, I actually want to see how you connect these two pieces together before I draw this out. So then I want to see how you do it. Have you to practice that?
Just draw a new bond.
New bond. Okay, yep. What does the carbonyl oxygen become? This carbonyl OH here become?
Just alcohol, like
Uh-huh. Neutral alcohol. Okay.
yeah.
And what is gonna be attached to this new bond? This is the new bond here to this carbon. What's attached to this carbon? What
It's
atom?
gonna be a hydronium because you're gonna have wait, no. Isn't it just gonna be like I don't know how to explain it. Just like draw OH and then
And then that R
draw
group.
yeah.
Yeah. And what charge would this oxygen have?
That's a really good question.
3 bonds.
Is it yeah, it's plus,
Yeah,
right?
plus charge. Yes.
Okay, I see how I messed up. Okay.
Mm-hmm.
Oh, that's because I assumed it was carbon. Okay.
Yeah. You connected this carbon with this carbon, right?
Yeah.
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 Because you thought this carbon is the nucleophile, but it's not the nucleophile. This oxygen is the nucleophile, so that's why the oxygen is attached to this carbon here with the new bond, like that,
Got it.
right? And everything else is
Yeah,
still
that would
attached
have
to the
made the
oxygen.
deprotonate and protonate so much easier.
Yeah. Now we do the protonate, deprotonate. this neutral oxygen here deprotonates that positive charge oxygen, which means that it will get protonated to give us this new intermediate right here.
No wonder
Wait,
it
let
looked
me
wrong.
see
I was like, this looks so wrong.
Yeah. I want to see what you tried after. Let's see. That connected that.
Well, I got the process right. I just
Uh-huh.
had the wrong nucleophile.
Yeah.
That's why it
you
looks
both had
so ugly.
Oh my gosh.
I know. I really did something. I just
Oh my
made me.
gosh. Oh my gosh, this is bending my mind. Okay.
Yeah.
Yeah. So we found the mistake at the very beginning. Well, not the very beginning. The first part was correct. After that, the nucleophile was
Yeah.
wrong. Yeah. I was like, this is some other like dark chemistry going on here. Let's see. OH, OH2 plus, OR, that's neutral. Okay. Now we're gonna reform this carbonyl, kick that out. And we're gonna have this intermediate right here. Positive charge, neutral OR. Now, the last step is to deprotonate with the HSO4 minus, yes. To give us our final answer, which is this neutral ester.
Yeah, that looks way better.
Right here. Yep. And we see that we substituted this OH of the original reactant with the OR of the nucleophile. The hydrogen goes away from this proton transfer step, right? We deprotonated that oxygen in this proton transfer step. So that's a quick way for you to predict the product. If this was a predicted product, not mechanism problem, you could just substitute the entire leaving group with the nucleophile minus one hydrogen to get the final answer quickly without doing the whole mechanism.
I see.
Right, and the name of this reaction here is going to be Fischer, Fischer, right? Fischer esterification. Esterification. It's just the name of this process, meaning that the original reactant molecule is going to be a carboxylic acid, COOH. The reagent is going to be some alcohol in acidic conditions, and then the product is an ester. So we're basically creating an ester from a carboxylic acid, alcohol, and acid. That whole like process that we just did right here, the name of that process is Fischer esterification. That's different than transesterification. Transesterification means that we're creating a different ester, different ester from an ester, right? This is not an ester, so this is not transesterification. That's carboxylic acid. Right. Okay. And another conceptual thing about this is that Fischer esterification can only be in acidic conditions. Only in acidic conditions. It can never be done in basic conditions. The reason why is because if I were to give you a carboxylic acid here, and we try to do Fischer esterification in basic conditions with that alkoxide ion, OR minus, with this solvent, alcohol, if you try to do Fischer esterification by having this strong nucleophile attack the carbonyl right away, that would not happen first, right? What's gonna happen is that this is a strong base, this is a strong acid. We're gonna do an acid-base reaction. We're gonna deprotonate the carboxylic acid to get the carboxylate and the neutral alcohol. So an acid-base reaction is gonna happen first because acid-base reactions are one of the fastest reactions you have in OChem. Acid-base reactions, very fast. Very fast. Right, so we're not gonna do a addition-elimination mechanism. That's slower than acid-base reaction. An acid-base reaction is gonna happen way faster. That's why Fischer esterification can never happen in basic conditions. Okay, yeah. So that's a conceptual thing which could be tested in multiple choice or explanation problem for Helix.
Helix has multiple choice?
Yeah, he has multiple choice, and they're more conceptual, like why does this happen, why does that not happen, and he has explanation.
Like, can you give me an example? Like, he just asks like why this happens?
That's for explanation, like why this happens, why this cannot happen. For multiple choice, it would be like what reaction has this intermediate, and he gives you a list of reaction names as the answer choices. Or he could be like, what reaction has syn addition or anti-addition for 1A and B, and then he gives you a list of reactions for the alkene reactions. For 1A and C, the carboxylic acid ones, he'll be like, which one of these reactions can not happen in basic conditions, and then he's gonna say like Fischer esterification, transesterification, hydrolysis, Hoffman rearrangement, and the answer would be Fischer esterification. That cannot happen in basic conditions. So that's the thing. You gotta know about these things conceptually, which we will go over in lecture. Right.
Okay.
And I'll go over them too. But I want to focus on the big reactions, mechanisms, and synthesis first, and after that we could focus on everything else, like the conceptual stuff, acid-base stuff, nomenclature stuff. And like those small things, like even though like they're worth less than the reactions, like mechanisms and synthesis, they do matter a lot because they build up like nomenclature, acid base.
Okay.
Okay. Kelly, did you get these problems?
No.
No. Okay. Oh, do you know what reaction we're gonna do for the first one here? First set of reactions here.
Hold on.
Okay. This is a secondary halocane.
The E1? No.
It's
E1?
E2.
2?
Yes, E2. This is a small, strong base, strong nucleophile. This is a bulky, strong base, strong nucleophile. So I'm gonna draw out two different hydrogens for you to grab, HA or HB. Let's look at the first reagent, the small, strong base, strong nucleophile. What is that gonna grab to create the correct product?
Brian, I can't concentrate right now because I'm driving.
Oh, you're driving? Oh my gosh, what the heck?
Really? Why are you on office hours while driving?
I just started. I have to go charge the stupid car at the ARC because the ticket guy was staring at me as I was going around, waiting to give me a ticket.
Oh my god.
So I had to go back, and now I have to go back.
Were you in the car the whole time?
No, I was at home, and then I just came out like 5 minutes ago.
Where do you live?
I'll answer that later.
Oh my gosh.
Oh, yeah. Sorry, I didn't mean to sound creepy. I was like, that's...
No, it's okay. I just don't know where I'm going right now.
Right, so let me just explain this really quick, and then I could stop the recording and then we could talk about that. Okay. So this small, strong, very strong nucleophile here is gonna grab the more substituted hydrogen, create the more stable alkene, kick out the leaving group for the Zaitsev E2 product. Right, and the recording will be up later so you can review this. The bulky base is gonna grab the less substituted hydrogen, create the less substituted alkene, kick out the leaving group to give you the less stable alkene, the Hoffman E2 product. This dash methyl here stays the same because nothing touched that carbon. Now the next one here is alcohol dehydration because we have an alcohol with acid and heat. The first step is to convert this bad leaving group, OH, into a good leaving group, oxonium ion. And once we have that good leaving group right there, we're gonna just think of this as an E1 type mechanism now, where the leaving group is just gonna leave by itself. It just goes away. It just goes off by itself to form a carbocation rearrangement. And whenever we form a carbocation intermediate, we form a carbocation intermediate. Whenever we form a carbocation intermediate, we always have to look out for carbocation rearrangement, like a hydrate shift. And we see that we could do a hydrate shift on the right? The left side here has no carbon, hydrogens, so we can't do a hydrate shift there. So we're gonna move that hydrogen over to that carbon to shift the carbocation to the more stable position right here. And then we're gonna grab the most substituted hydrogen, which is HA, to create the more substituted alkene as the final product. Like that. Okay. Yes. Okay, so that is it. That is alcohol dehydration. and E2. Two big ways to form alkenes, but there's like more examples that are tricky than this, but I'll wait until I see get the lecture slides to see how she teaches this. Okay, let me